All right, so we're going to keep talking about electrochemistry here. A little bit of review. We talked about how if a chemical reaction has a delta E, or not a delta E, I shouldn't say delta E, just an E value, where E is not energy here, but E is what we call the potential. All right? And if we have a positive potential, then that means we're going to have a negative delta G. All right? So just like a negative delta G means that a chemical reaction is spontaneous, a positive E, or E cell, where E is the chemical potential, is an indication of a spontaneous reaction as well. And again, if I have a given chemical reaction, for example, zinc combining with copper ion to form zinc ion and copper metal, put a 0 there, all right? This sort of a thing, we can find out we can look at the reductive half reactions for zinc and the reductive half reaction for copper. Now, reduction means that we're gaining electrons. So here you would have the copper ion gaining 2 electrons to form metallic copper. And we would also have in our table of reduction potentials zinc ions gaining electrons to form zinc metal, metallic zinc. All right? And then in our table of reduction potentials, we'd be given a value. For example, negative 0.321 and, well, I'm going to call this actually a positive, and negative 0.810. All right? So this is just an example of how you might find a table of reduction potentials, and given a chemical reaction that's a redox reaction, we can identify what the E cell for this reaction is by looking at the table of reduction potentials. So what we do is first we look at this reaction here and find out which one of these is occurring just as it's written in this reaction. And we can see that this zinc one here, 2 electrons, whoops, this needs to be a +2 up here, 2 electrons going on to the zinc 2 ion. This isn't what's happening in this reaction. Actually, the reverse is happening in this reaction, right? We have zinc metal giving up 2 electrons to form zinc ion. So this is not the one that is happening in this reaction. However, the reverse is happening. This one up here is what's happening in this reaction. We have copper ions taking electrons to form copper metal. So this reduction process is occurring in this reaction. So I'll take that value, which is a positive 0.321. All right. This reaction is not occurring up here, but the reverse is. So I can take the opposite of that value, which is a positive, I'm just going to add these two together, a positive 0.810. And then the resulting E cell, or potential, for this reaction is going to be the sum of the values there. Okay? Now again, they say cathode minus anode, anode minus cathode. Don't have to worry about that. All you have to do is identify which is occurring and which is not occurring. And the one that's not occurring, you just got to flip it around to show that it's occurring. And then when you flip these, you change the sign. Okay? Now, an interesting thing about these chemical reactions, which I should tell you, is these are E naught values, or their standard reduction potentials. So if I had this process occurring, it would contribute a 0.321. If I put a 2 in front of all this, or double it all, then it's still a plus 0.321. It doesn't double, because this is considering that you only have 1 molar of this material. And so it's a little bit confusing. Why doesn't that double? But it doesn't double. So unlike the delta H, when you double the values here, your delta H for the chemical reaction doubles. But the way reduction potentials are provided, they're just values for a given reduction half reaction. And this value here doesn't correspond to these coefficients here. It just corresponds to standard conditions, which is 1 molar. All right? So now, if I had a different chemical reaction, let's say we have a zinc metal plus a gold plus 4 ion. All right? The products of this reaction we're suggesting will be a zinc plus 2 ion and solid gold. All right? Now, I can look at my reduction table here and see that I can still use this value. I don't have any information about the gold, so let me add on to this reduction table a second reductive half reaction. So we're going to say we have Au plus 4, taking 4 electrons and going to Au, and I could say that this has a value of positive 0.118. All right. Now, if I wanted to find the reduction potential for this reaction, I could, again, find out which one of these is occurring, and I see that this one's occurring in this reaction. So I would take my 0.118 and add it to, looks like the reverse of this is occurring, right? So add it to a positive 0.810, and that would be my E cell for this reaction. Okay? Now or before I do it or whenever, I might note or I might see, wait a second, this equation is not balanced. It's not balanced because zinc is giving up 2 electrons, but each gold ion is supposed to need 4 electrons. We can balance it by adding twice as many zinc ions as gold ions, and we might be tempted to try to change this value right here because now we have 2 of these, but it doesn't change. It doesn't change that value because, again, the E naught means that you're working under 1 molar conditions. Okay. Now, yes, it's true that this is 2 to 1 ratio, but in solution it would mean you'd only have 1 molar of this and 1 molar of this, because that's an ionic compound, and 1 molar of this in solution to give you the E naught E naught that would be produced by the combination of these 2 redox potentials. All right. We also talked about this relationship here. Let me see this one here. Our delta G can be related to our E through this relationship where, let's go back one more slide here. E can equal RT ln of K. Negative RT ln of K is our delta G, right? So, back one more here. Delta G equals NF E, all right? Again, our free energy is related to our overall cell potential, N being the number of electrons that changes hands. What's the delta N for, let's go back up to this reaction here. What's the delta N for this reaction here? Talk to your neighbors really quick. Identify what the delta N for that reaction is there. 60 seconds. All right. So I can see here that zinc is, we're looking for delta N, where N is the number of electrons transferred, right? So zinc here is losing 2, copper is gaining 2, so the delta N is 2. All right, how about this one here? What's N? The number of electrons transferred in that reaction? 10 seconds. Talk to your neighbor. Tell them why you know what you know. All right, the number of electrons that zinc loses here is 2, but there's 2 of the zinc, so that's a total of 4, and gold is gaining 4. So this N value is going to be equal to 4 here. All right, this other equation here that relates the equilibrium constant that we've talked about in various chapters before to our E value. All right. Very good. So a couple of equations that you can be familiar with. I think the likelihood of actually having a problem where you have to use these equations is very slim. But all right. Now, there are chemical reactions, galvanic cells, where you are actually making energy. And then there are chemical reactions called electrolytic cells. Electrolytic cells, where you are driving a process with electricity from some other reaction that is spontaneous. In an electrolytic cell, you're using a spontaneous reaction to drive a non-spontaneous reaction. All right? And this is how all metal is made, right? Because metal, although some of it is relatively stable, and you know, you can dig in the ground and still find things like silver and gold and platinum, but beyond that, there are stores of copper, for example, in the earth are significantly lowered. We don't have very much copper left in the earth, and other metals like lead and zinc, those are too reactive to have any significant amount of them found in the metallic form ever, right? So anytime you see any metal in any part of the world, right, you can almost rest assured that that metal was pulled from its salts to its metallic state, right? Or in other words, you had some sort of a chemical reaction where you had the metal ion and electrons were given to it to form the metallic metal. All right? Now, this type of a process is called an electrolytic cell. All right? It's not a cell that produces power. It's a cell that requires power to occur. So here are some differences between our electrolytic cell and our galvanic cell. Our galvanic cell is what we've been describing previously. It's basically the battery that we've been drawing, where we have an anode and a cathode. So I usually like to put my anode on the right. So we say this is our anode here, and we have our cathode. All right? And we should do a little review here as well. We remembered that we have some sort of a metallic thing here, and that there's an electrode here as well, right? So this is our anode material, this is our cathode. And we have to talk about what is occurring at the anode. Well, hopefully you remember that anode begins with a consonant, and the process that occurs here begins with a consonant as well. That's oxidation. All right? So that means at the cathode we have reduction occurring. All right, so here some metal ions of some sort are getting electrons from this surface and being reduced. Okay? Over here, oxidation is occurring. These metallic atoms are giving up electrons and becoming some sort of an ionic metal. All right? Now, this process allows electrons to flow from the left side over to the right side, because electrons are leaving here and you have electrons moving in this direction. All right? Now, we have a sign notation for the anode and the cathode. And I don't know if you guys have gathered this, I'm sure, and you know that in a battery, right, there is a positive side and a negative side, and we use those signs to help us know which is which, right? And nobody really knows which is which in terms of, you see it you ask people in the street, which side's the positive, which side's the negative. People don't know. But that's okay. They don't need to know. They just stick this thing where the machine says you want the positive, right? If you stick it into a device and it doesn't work, you flip it around and it works, right? So it's not like it's a huge problem. Now, if you're dealing with a car battery, yeah, that's a little bit more of an issue. However, things are clearly identified for that sort of process, right? But we have identified that in a galvanic cell, a battery, something that produces power, we call the cathode the positive and the anode the negative. All right? Now, this is worth very little, in my opinion, in terms of trying to remember which is which. This is important to know that at the cathode, reduction is occurring, and at the anode, oxidation is occurring. The reason why this cell configuration, and again, this was just a couple people who got together and said, hey, we'll call one positive and one negative. Now, they were trying to talk about where electrons were going to be moving, sort of thing, right? And think about the charges on these electrodes. Now, here you can think of the electrons moving this direction, and so electrons kind of you could think about them building up here and trying to jump off onto ions. And so you might get confused into thinking that's the negative, right? This, again, is what they've defined as the cathode positive, and the anode is negative. All right? So, the cathode is defined as positive, the anode is defined as negative. Why do they call that positive? To me, it seems backwards, and to half of the people who are trying to decide how they should label it, it seemed backwards at the time. But, there's just a bunch of people who kind of essentially voted or bossed each other around until they decided, okay, we'll call the cathode positive. All right? So, what was the reasoning behind the people calling the cathode positive? Well, what they were saying is that these electrons are being drawn to this side. So these negatively charged electrons are being drawn to this side, and it's a positive side. Okay? So then, that says that the cathode is positive if the process that's occurring is an electrolytic cell. One thing I kind of forgot to draw was our salt bridge. We'll draw that in. But so if it's an electrolytic cell, or sorry, not electrolytic, but a galvanic cell, a cell that's producing power, then the electrons move from anode to cathode, and that movement, you can think of these electrons being drawn to the more positive side. All right? But you see in an electrolytic cell, the cathode is identified with a negative value, and the anode is given a positive value. So what's occurring there? Well, in an electrolytic cell, it's like charging a battery. So what we would have to be doing here is we would have to be taking these ions, right, and giving them electrons, so that it would form the metallic material here. All right? And as the electrons are being given, let's see, are we doing that right? Nope, sorry, that's not right. Because here, the ions are coming and getting electrons. So what we're doing here is we're taking these metallic material here, this metallic metal, and we're taking its electrons away from it and making the ions. That's what we're doing there. And so when you do that, this here, electrons flowing to left to right, anode to cathode, is called the galvanic cell. That's a battery. That's how a battery works. But if this is going to be an electrolytic cell, it's what you need to do if you want to make metallic metal from its ions, or charge a battery. Charging a battery is an example of running a cell electrolytically. You are pushing electrons to go the opposite direction. So an electrolytic cell, electrons, travel from cathode to anode. So this is electrolytic, all right, or charging of the battery. So all you have to remember, essentially, is that the anode is where oxidation occurs and cathode is where reduction occurs in the galvanic cell. All right, if you just remember that, and then you think about the electrolytic cell, the charging of it being opposite, now these electrons are going to be running towards this side. So in a galvanic cell, your anode is negative and your cathode is positive because the directions to where the electrons are being kind of drawn is where this positive and negative configuration comes from. In the electrolytic cell, however, electrons are going the opposite direction, and so you say that the anode is the positive side and the cathode is the negative side when you're talking about a cell that is, electrolytic. All right? So that's a lot of explanation for probably a slim amount of use, but I think I remember seeing one question a while back. I can't remember if it's on any of the exams that you might be taking, but it talks about electrolytic cells versus galvanic cells and their charges and so forth. All right, so there's a couple of ones that we're not going to go over here, but we're going to get into this relationship here. Because this is something that we can use our old toolbox, our old tools, understanding of relationship between chemical reactions and number of electrons and moles of material to answer simple questions about electrolysis, or another use of this electrolytic cells is electroplating. Electroplating means putting a surface of metallic material on the outside of something else, right? So chrome plating is an example of electroplating. You can plate silverware with a shiny surface. You can plate any type of jewelry with a shiny surface. Cheaper jewelry is often some cheap material plated with a different shinier metal on the outside. Even the pennies that we have nowadays are not 100% copper. It's zinc, which is relatively cheap, plated in the more expensive copper, so we don't have to use as much copper. All right, so to be able to understand how to answer questions like how long is it going to take to plate a 1 millimeter surface over this bumper on my car, right? To answer that kind of a question, we need to know about the other part of power. Power is the potential times the current. Potential times the current. So power is the potential. So this is like the E cell that we were talking about before. And then I here is the current. All right? Potential is in units of joules per coulomb, and current is in units of coulombs per second. Coulombs per second. All right? Coulombs are a unit of charge, and you don't have to remember much about coulombs. There's this constant that is utilized. It's 96,500 coulombs per mole of electrons. It's called Faraday's constant. This is going to be used in plug and chug scenarios, or when you're trying to relate how many moles of electrons there are for every for the number of coulombs, right? 96,500 coulombs for every mole of electrons. Also, you're going to be using it when you're defining what current is and wondering how much time it's going to take, because a unit of current, is coulombs per seconds. Now, coulombs per seconds are also known as amps. So, amps and potential is in units, joules of coulombs is in units of voltage. And voltage times amps equals watts. All right? So there's our power, there's our voltage, and there's our current. All right? Now, current is coulombs of charge for every second, and there's 96,500, that's Faraday's constant, coulombs for every mole of electricity. All right, so electroplating, we can use this information. We can use, if we know the current, then we know how many coulombs per second will be provided. And if we know that a coulomb or amp is coulombs per second, if we know that an amp, or that a coulomb is 96,500 electrons for every mole, 96,500 coulombs for every mole of electrons, then we can know how many electrons for every second as well. All right? So we'll see how this is used. So here's our first question that we're going to work through together, and then the second one there you guys can work on with your partner. What current must be applied? All right, so what current? Now, this is our process here. We want to be able to remember that current, current, which is the letter I, is coulombs per second, which is the same as amps. All right, so how many coulombs per second need to be applied to deposit 3 grams of gold from a solution of gold chloride if we want it to be applied in a time of 200 seconds. All right, so we can use our old tool of dimensional analysis to answer this. We just set up an equal sign and a line like this, and we identify what we're looking for, what current. So the current is how many coulombs for every second do we have to add, that's the question. How many coulombs per second if we want the following process, 3 grams of gold, right? Convert that 3 grams to, I know which way to start here, but you might not know, so we can work from back here. We can see that we want to have coulombs up here, coulombs of electricity here. We want seconds down here. Seconds can be in the form of, it says 200 seconds. So we want 200 seconds to be the time frame for us. How many coulombs? Well, we know that there are 96,500, let's see, that's Faraday's constant, 96,500 coulombs for every mole of electrons. All right, so there's 96,500 coulombs for every 1 mole of electrons. All right, and so now we can maybe see we want 3 grams of gold, but that 3 grams of gold is going to come in the form of Au plus 3, getting 3 electrons and forming Au solid. All right, that's what we're asking to happen. So if we identify how many moles of this material, we'll know how many moles of this. Because this to this is a 1-to-1 ratio, this grams of gold can also be thought of as 3 grams of Au plus 3 ion. Now, how did I know it was this? How did I know that it was gold ion with a plus 3 charge getting 3 electrons to form this? Well, because I look here and I see that this is the ion that's available to us from gold chloride, and there's 3 chloride ions, so that must be an Au plus 3 charge. Okay, so 3 grams of gold, I can use the molar mass of gold. How many grams of gold for every 1 mole of gold? All right, I need one more thing in here. After I have that, I'm not going to be able to sneak it in. I have one more slice in here. On the top, I'm going to have, let me just show you. Oops. There we go. Let me just bring it up here. So we identify how many moles of gold I need, and then I can see that for every mole of gold, I need 3 moles of electrons. All right, so that's the one I was going to fit in here, but I just can't fit it there. All right. So for every mole of gold, I need 3 moles of electrons. All right? So I took the grams of gold, find out how many moles of gold that is, and that tells me how many moles of electrons. For every mole of electrons, I need 96,500 coulombs, and that tells me how many coulombs I need. Let's see, that's how many coulombs I need, and current is coulombs per second. So if I, let's see, Why do we have this multiplied by 200 there? Oh, there it is, 22.1 amps. 22.1 amps. So I'm taking this 4410 and dividing it by my 200 seconds to get my amps. And that's the question that was asking, what current? And my current is going to be in amps. All right, so the next question here, it asks you something slightly different, but the same type of thing. The tools, the new tools that we're getting here is that amps are coulombs per second, and that there are 96,500 coulombs for every mole of electrons, right? For every mole of the ion that you want plated, right? You need to recognize how many electrons. And in this scenario here, this second one down here, we see that there are silver ions that we're going to, how much time does it take to plate 10.2 grams of silver ions? So the Ag plus, for it to become silver metal, right, we can see that it's going to take just one electron. All right. So these are the kind of the new concepts that, this one's not very new, we've seen that before, but these are the new concepts that we need to answer this kind of question. So to the right of your equal sign, it says how much time, seconds. So I'm looking for seconds here. All right, so I want to know how much time it takes to plate 10.2 grams of gold using 0.1 milliamps. 0.1 milliamps. Now, 0.1 milliamps, that means you can think of it as millicoulombs per second, milliamps, right? Or instead of 96,500, well, milliamps is just millicoulombs. Coulombs per second. Milliamps would be millicoulombs per second equals milliamps. There we go. And if you wanted to convert coulombs to millicoulombs, you would just divide this by 1,000, and then that would be for every millimole. All right? Or you could think of millicoulombs. There's 1,000 millicoulombs for every 1 coulomb. Okay? So given that much information there, see if you can work with your neighbor now for a bit and try to identify how to fill this in to answer the question. Okay? Give yourself about 90 seconds for this one. All right, how are we doing? Okay, so we're going to plate 10.2 grams of the silver, Ag, right? And we could think of that, you know, if we change it from silver to silver ions, that's the same thing, because it's the same mass. If it's ions or metallic, the difference of an electron doesn't make a change in mass at that scale. So 10 grams of gold, we can go grams of gold to moles of gold, and for every mole of, sorry, not gold, silver, for every mole of silver, that's 1 mole of electrons, All right, and I know that 1 mole of electrons is 96,500 coulombs, and they told us that we're going to have 0.1 milliamps. 0.1 milliamps, that's equal to 0.1, I should go first, I can just go 0.0001 amps, right? Which is the same as 0.0001 coulombs for every second. Okay? So if I have 96,500 coulombs, I want coulombs down here, 0.0001 coulombs for every 1 second. And that's going to tell me right here how many seconds I need to provide that many electrons. I think this is 107.9 grams for every mole. So, all right, so we used our dimensional analysis. This was easy here. This is not too bad. For every mole of silver that's going to electroplate, we need a mole of electrons. This is our new constant here. Faraday's constant says that there's 96,500 coulombs of charge per mole. That's a constant which will be provided for you. And once you see you're in moles and you need to get to use current or anything like that, you'll have to also remember that amps is a unit of coulombs per second. I even think that this is going to be information that's provided for you in the equation portion of the exam. All right, so 96,500 moles or coulombs per mole, and then current that's provided. They told us how many coulombs per second by telling us that it was 0.1 milliamps of power. All right, so 9 times 10 to the 7th seconds to electroplate that much metal. Okay, so here's one more. Let's take the opportunity to do this one. All right, so you and your neighbor work together on this one. Give you about 90 seconds. Go. All right, so let's see how you did. If we start off with the, well, first we recognize that we're after seconds. Set up our dimensional analysis here. Start off with 1.5 grams of chromium. Now, it doesn't matter if you use chromium metal or the chromium ion, but you can recognize that there's how many, and we can identify how many moles of chromium we have, and then also how many moles of electrons are necessary. I identified the moles of electrons necessary because I can see that we're going from a +3 to the metallic form. And that looks like this. Cr +3 going to the metallic form. I must be adding on 3 electrons to get that done. All right, so that's where I got this 3 moles of electrons for every mole of chromium. And then for every mole of electrons, that's 96,500 coulombs. That's Faraday's constant. Faraday's constant is 96,500 coulombs of charge for every mole of electrons. All right, and then after I'm in coulombs, now I just have to get how many seconds out of coulombs by utilizing their information about 50 milliamps of current. 50 milliamps of current, that's equivalent to 0.050 amps of current, and an amp is 0.050 coulombs for every 1 second. So then I can use, for every second, you're going to get 0.05 coulombs, and then that should give me my answer there. I'm not going to need this 0.744. This is a helpful piece of information just to see that I need the 3 electrons there. All right, so hopefully you guys got the right answer there. Okay, so we talked a little bit about fuel cells, and now we're going to talk just a little bit about rechargeable batteries. All right, I already talked a little bit about rechargeable battery. I mean, I already talked to almost all I'm really going to say about rechargeable batteries. But you should recognize that all materials can be recharged simply by applying a different chemical reaction that's stronger, has a stronger potential to it, right? But rechargeable batteries in themselves don't necessarily save energy. A rechargeable battery that I use for an electronic device of some sort, when I take it and charge it up, I'm just charging it with oil, you know, for whatever source of electricity I'm utilizing. So the rechargeable battery itself doesn't save power. It just it can clean up emissions, for example, automobile emissions. If you have an electric car and you utilize your electric car a lot in the city, right? So here's the city where lots of people are going to work, and if I have an electric car in the city, right, then I'm not going to get as much pollution in the city, right? But to charge my electric car, right, I need to have this, and this needs to be connected to some of these, right? And this is going to be connected to some factory somewhere that is burning diesel fuel and creating the chemical reaction which is going to drive this process. Okay? So electric cars can have an advantage in that they reduce the amount of pollution in the inner city. Another good thing about them is a lot of people's cars don't run very efficiently. I mean, all cars run inefficiently. But if you don't change the oil in your car, if you don't, what else? Well, there's a variety of different things you can do to try to mistreat your car, right? The air filter, the quality of gas, this sort of thing. Then your car doesn't get very good efficiency either. If you have a diesel mechanic running the engines here at your plant that's supplying the electricity, now there is loss in the electrical wires themselves, which is a big deal. But if you have a diesel mechanic, then you can increase efficiency that way as well. All right, so rechargeable batteries also are called secondary batteries or secondary power sources. All right. Lithium-ion batteries are very promising. They're very interesting, and if you guys want to talk about them further, you can come by my office. We're not going to take much time today, though, to talk about them. The hydrogen fuel cell I talked about. It has very promising attributes, the best of which is that it only produces water as a byproduct. All right, and then we'll end up with this video that I was going to show you earlier, showing again a little bit about how we get metal from the mountains.
The Earth's crust contains
Whoops. Oh, what did I do?
The Earth's crust contains many compounds, but the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide. Split the aluminium from the oxygen, and you have one of the world's most useful metals. You can split a compound using electricity. The idea is to pass an electric current through it, a process known as electrolysis. A circuit is set up using 2 carbon electrodes, an ammeter, and a power supply. The white powder is lead bromide. Switch on the power supply, and nothing happens. The ammeter reads 0. Solid lead bromide doesn't conduct electricity. It needs to be molten. Lead bromide melts at 370 degrees Celsius. Switch on now, and a current flows. In this circuit, the electrode on the right is positive, the one on the left is negative. As electricity passes through the molten lead bromide, chemical reactions start. On the left, at the negative electrode, nothing appears to be happening. But at the positive, bubbles mean a gas is being produced. Placing small tubes around the electrodes traps in gas, making it easier to see their colour. What could the brown gas be? The gas is bromine. Although nothing obvious appears to be happening at the left-hand electrode, pouring the molten lead bromide away reveals a small silvery metallic bead. This is pure lead. So, passing an electric current through molten lead bromide breaks it down into the elements lead and bromine. To work out why this happens, imagine you can see the charged particles, the ions, in the compound. There are positive lead ions and negative bromide ions. Once the power supply is switched on, the lead ions are attracted to the negative electrode. The bromide ions are attracted to the positive electrode. Lead ions pick up electrons. They lose their positive charge and form lead atoms. Bromide ions give up electrons. They lose their negative charge and become bromine atoms. These form a gas. Electrolysis of lead bromide only works when the compound is molten. Why doesn't it work when the compound is solid?
Because the cell's not conductive. Alright, so
Change the compound from lead.
we're going to skip ahead here just a bit and show you the ramification of not finishing your degree. Alright, I think I've showed you this before, but I want to emphasize it. Here's what you do if you don't finish your degree. You end up working in a huge factory. Here's the huge factory where this process that was just described occurs daily, 8 hours a day, maybe even 12 hours a day. And there he is, wishing he would have finished his degree in college. Instead, he got a good factory job. Pays good, got a union and stuff, but looked kind of hot. And I don't know if you guys want to do that for 8 hours a day. So, very good. That is, let's see where we at here. That is our lecture for today. We're all done. We're done with Chapter 20, and so we'll start with Chapter 21 in the next class. All right. So, thanks for coming today. See you later.